Welcome to the lecture Feature Extraction in Frequency Domain. In this lecture we are going to talk about the frequency analysis of the speech. So basically we will try to understand the Fourier transform and its significance, and we'll try to study the Fourier transform of a speech signal, and then we'll try to understand the formants, one of the features or representatives of the speech signal. So before we try to dig in the Fourier transform and then understand or define the Fourier transform mathematically, let's try to understand why do we need frequency analysis first. So this has been my favorite question, which I used to ask in my earlier classes. So let's take a sine wave which is sampled at 16,000 Hertz, and then so the question here is, what is the number of bytes required to store a sine wave sampled at 16,000 sampling frequency? So the assumption you can make is the sine wave is 10 seconds long, and each sample takes about 2 bytes, that is 16 bits per sample. So how many number of bytes are required to store the sine wave with these conditions? You would like to think that you can it's simple to compute, and then you want to do this mathematical way, 16,000 samples per second, and then since it is 10 seconds long, then it would be 16,000 cross 10, and since each sample is with 2 bytes, then you want to multiply with 2. So that's a straight way of computing the number of bytes required to store the sine wave. Can it be more smarter? Can we do more efficient way of storing this? So let's look at the answer here. It takes about 4 bytes to store such a sine wave. So 2 bytes to store its frequency, which is denoted by W or omega, 2 bytes for its amplitude, denoted by A here. So if you know these two values, then you can plug in into the equation y is equal to A sine omega t, where t is the sampling instant or denotes time, and then you can generate the sine wave again, I mean for not only for 10 seconds, but you can generate for infinite amount of time. So all you need to store such a sine wave is to know these two values, the frequency of the sine wave and the amplitude of it. So this is a simple way to understand Fourier transform, or the power of the frequency analysis. Let's look at more examples here. So this is a sine wave, which signal in the time domain, so x-axis is time here, and then you can see that the sine wave has got one cycle in 1 second. So this is the time from 0 to 1 here, and in 1 second duration the sine wave completes one cycle. So this is a signal in the time domain. So if you take the Fourier transform of this sine wave, so what you would get is something like this, what you are seeing here. So this frequency, the x-axis is frequency here, and the y-axis is the magnitude, log magnitude. That's why it is specified in dB here. So we have sine wave here with 1 cycle per second, and its frequency analysis shows that there is a peak at 1 Hertz, which essentially represents the number of cycles per second in the time domain. So there is a peak at 1 Hertz. The 1 indicates the number of cycles that are there in the time domain. So you are seeing here this tail of the signal. This is the artifact of the signal processing. Otherwise, what you would want, or what you would ideally want to see, is a single point here, and then which shows that all the frequency component of this signal is represented or is stored at 1 Hz, which is there here. So 1 Hz is in the x-axis, and you are seeing a peak here, and this, the y-axis value, denotes the amplitude of the sine wave here. So let's look at more example, some more. So this is a time domain signal here, and this is a Fourier transform of it, and then we have 5 cycles per second, and then what we would expect is a peak at 5 Hz. That's what we get in this case. Since there are 5 cycles here, that is being represented in the Fourier domain or frequency domain, that it has got a peak at 5 Hz. Again, this tail is the signal processing artifact, so ignore this tail, only concentrate on the peak which is obtained at 5 Hz. Now it has got 30 cycles here in the time domain, and then you would expect a peak at 30 Hz. That's what you get. So this is a very simplistic way of understanding the Fourier transform. A Fourier transform would take a signal as input and give you the frequency components present in the signal. The dominant frequency component of the signal could be observed as peaks in the frequency domain, and typically a frequency domain representation of a signal is referred to as spectrum. So let's look at more into the diagrams which we have seen earlier. So there are 2 signals. This is one signal here with 5 cycles per second, and then that's, you are getting a peak at 5 Hz. This is another signal which with 70 cycles per second, and then you are getting a peak at 70 Hz here. So this is the frequency axis, which is denoted by these 2 arrows here. So this frequency axis, the initial portions are called low frequency region, and then as you go further into the frequency axis, the more you go, they are called higher frequency components or higher frequency region. So what is the significance of it? So a peak in a low frequency region indicates a slow varying signal in time domain. That means if you have a peak at 5 Hz, that shows that you have got a 5 cycles per second signal in the time domain. That means when you compare this 5 cycles with 70 cycles, it is a slow varying component or slow varying signal. And similarly, when you have a peak in the high frequency region, that indicates a high varying or fluctuating signal in the time domain. So here you have a peak at 70 Hz, and then you are seeing a 70 cycles per second signal in the time domain. So what essentially it means that when you see a peak in the higher frequency region, you are going to get a highly varying signal in the time domain, and when you see a peak in the low frequency region, you are going to get a slow varying signal in time domain. So let's go into more formal definitions of Fourier transform, discrete Fourier transform, fast Fourier transform, and relation between DFT and FFT. A Fourier transform is a representation of a sequence in terms of the complex exponential sequence, where e minus j omega n, where omega is the real frequency variable and n denotes the time variable. So that means that given a signal, it represents or